Welcome back to Quantify Your Career. And today, let's talk about a foundational concept in linear algebra called Gaussian elimination. Suppose you have a messy set of linear equations which you would like to solve step by step. That's where Gaussian elimination comes into picture. It is a systematic way to simply solve a messy set of linear equations and also give you the results accurately. However, its applications are not just in solving these linear equations, but also in matrix inversion and also finding determinants of matrices. In finance, however, it is used in solving for constraint optimization problems. So, one of the applications can be finding out portfolio weights in mean variance optimization. And this is one of the numerical techniques that is used. It also finds its applications in fluid dynamics and circuit analysis. Now, one of the limitations of this technique is that it lacks efficiency. That makes it tough for solving large matrices if you have a lot of equations. Now, let's learn this technique with an example and also see how it is implemented in Python. Watch till the end for a bonus interview question. These kinds of questions are seen in quantitative finance and even data science interviews. Now, let's try to solve this using an example so that you can understand how the math works. Now, suppose you have three equations. Now, what is the first step? It is to convert this into a coefficients matrix. Something like A is 2 minus 3 minus 2, 1 minus 1, 1 minus 1, 2, 2. This forms the coefficient matrix. And then the B can be 8 minus 11 and minus 3. A is the coefficient matrix of these set of equations. So now what we want to do is we want to create an upper triangular matrix, meaning everything below a diagonal has to be 0. So if we make this augmented matrix like this, we will first normalize the first row. So divide the first row by 2. That gives us this matrix. And everything else remains the same. Now to create something called a pivot 1, what we do is leave the first row as is, but perform this operation where row 2 plus 3 multiplied by the first row. So if the first row remains as is, the second row now becomes 0, 0 0.5, 0 0.5, and 1. This is coming from minus 3 plus 3 multiplied by 1, which gives us 0, minus 1 plus 3 multiplied by 0.5, which is 1.5. That means it's equal to 0.5, and similarly for the other elements. And again, the third row remains the same. This is actually pivot 1, where you multiply 3 with the first row. Next, you want to get everything below this diagonal to be 0. So next you want 2 to become 0. So that's why repeat what you did here, but now divide the second row by 2 to normalize it. So that makes it, this first row remains the same, but the second row is divided by 2, and the third row remains the same. And lastly, row 3 minus 2 multiplied by the second row. And that will give you 1.5.54 0, 1, 1, 2. The first two rows are the same. Now the third row becomes this. So now everything below the diagonal is actually 0. So this was forward elimination. Now next comes backward substitution. So now if you translate this matrix back into equations, you will have x plus 0.5y minus 0.5z equals 4, y plus z equals 2, and minus z equals 1. So with backward substitution, you get z equals minus 1, y equals 3, and x equals 2. So this is how Gaussian elimination solves these set of equations. Now, let's see how we can implement Gaussian elimination in Python. Okay, so here we have a function called Gaussian elimination. We will solve the equation ax equals b, like I had shown in the previous example. First, we convert matrix A into an array and into a numpy array, and B into a numpy array as well of type float. Now n indicates the number of equations. So in our case, it'll be 3. Moving on with the forward elimination, first we need to find the rows with the largest absolute value. Here, we need to find the rows with the largest absolute value in column I, starting with row I. What basically we want to do is we want to ensure that the pivot should be as large as possible. So we will swap rows if the pivot is not larger than the next row. So you swap rows like this if the current row is not the maximum row. Next, we extract that pivot element from row I. Now remember that if pivot is equal to 0, that means your matrix is singular and it cannot be solved. Because how would you multiply and add or subtract if that pivot itself is 0? So we raise a value error that the matrix is singular if the pivot is 0. Next, we normalize the pivot. We divide the entire row with that number. If you remember the way we had divided row 1 with pivot with number 2. Next, we eliminate those rows. We eliminate the current column in rows below the pivot by subtracting a multiple of that. If you remember, we had added 3 multiplied by the first row. That's what we are doing here. This is to make the first column 0. And then the subsequent columns till all the numbers below the diagonal are 0. That is the main goal. That's what this section does here, row by row. And once you have the matrix and you have the upper triangular matrix, you then do back substitution, where you initialize this solution vector x with rows with zeros, and then work backwards from the last row, since there will be only one element remaining in the last row. And then you work through to the first row, and then for each row you calculate the solution. And this numpy is np dot dot is for vector multiplication. And finally, a solution is returned. So for example, if A is a matrix which I had shown earlier, and B is that matrix which is on the right hand side of the equation, you get the solution vector as x, y, and z equal to the actual values which we had solved earlier. A bonus interview question related to Gaussian elimination in linear algebra can be talk through some of the limitations of this technique and how you would solve this. And one more question could be, when would you not use Gaussian elimination, or when does it actually break? Like I had mentioned, if the matrix is singular, it cannot be used. And we had addressed limitations earlier. Let me know on what do you think are some of the limitations of this technique and how you would solve them. So I hope you've understood this technique since this is a basis and foundational concept of linear algebra. Let me know if you have any questions, and I'm happy to address them. Until next time.